All right, thank you everyone, and sorry to be keeping you from lunch, so I'll try to go through the material as efficiently as I can. My name is Jonathan Raymond. I work on large-scale reinforcement learning and generative models at NVIDIA. I lead a team in this area, and I'm going to be showing different work, some of them from there, some of them from other places. So it's just sort of a broader overview on things. So the topic that I'd like to talk about today is reinforcement learning frontier, and sort of how are we pushing the limits, what's sort of happening in the land of reinforcement learning kind of over the last few years and where it's taking us right now. There's a lot of areas in which we've seen sort of great success of reinforcement learning systems, but they've had all sorts of really special aspects to them that made them successful. We've got works that have happened in board games, works that happen in more industrial cases, mathematics, things like that. And each one of them sort of brought along a specific set of challenges. And really, when we look at the bottom row, we're starting to see things that we get to use day to day, like ChatGPT or Claude or DeepSeek or Nemotron models, things like that. I want to kind of go deeper into what it takes to do this. Let me just make sure it doesn't autoplay. So the talk's going to go the following way. I'm going to first kind of go over a few ideas on like what reinforcement learning is so that everybody has a bit of a shared context. And then I'm going to go more into things that have been sort of success stories or ways in which we've cracked things in reinforcement learning. And after that, talk a bit about what's not working and where we're going with things. And because this is all part of the open source AI week, I think one of the topics here is going to be a bit about what's happening in the software and infrastructure landscape that's going to help us kind of push these things forward. So to begin, one of the important concepts I think that's important to know about reinforcement learning is that it's a series of algorithms that are generally quite sample inefficient. There's a lot of things about it that are not desirable, but we mostly look for it because there's places in which we don't have a solution. We don't have the plan for how to get from a point A to a point B. So that's why I'm sort of showing a maze. We're in some world and we don't know necessarily what's the series of turns or ways in which we're going to get to an endpoint. And so what we look for is this sort of emergence, right? The ability for reinforcement learning systems to discover solutions that we don't necessarily have. And we can tell them whether they did a good or bad job, but we can't necessarily give them the solution at the beginning. So the important piece that kind of makes these things work is what we call credit assignment. So when we have a problem and you take a series of moves, even if they're random, at some point I can tell you whether or not you did a good job. And it's also important to let you know which of the specific moves you made mattered. And the way that we do this in reinforcement learning typically is that partway through your journey, let's say in this maze, we will try to ask models to predict how well they're going to do in the future, whether or not at this point they've made some progress towards a goal. And based on that partial progress, we can then use that information to say that that was the place where this move made it advance forward, and that's the one that should be credited with the improvements. So credit assignment is basically this. It's the return based on future rewards, and we're going to measure this empirically and then use that to compute a function that predicts that advantage that we're getting from each move. Unfortunately, we have a bit of a kind of a chicken and egg problem in reinforcement learning, where at the beginning of the problem, we don't know what the right actions are to perform, right? So we sort of start with no knowledge about the world or what exactly we're supposed to do. And on the other hand, we also have rewards. And in many places, I might be able to tell you if you played a game of chess at the end that you won the game or you lost the game. But if you're just moving a pawn in the middle, what's the reward for that, right? It's sort of a bit of a blank slate at that point. And that's also what we're learning in these problems. So if we had perfect rewards, problem would be maybe a lot simpler. And if we had known actions, we'd all be kind of much farther along. But we have this issue where both sides are kind of unknown at the beginning. So generally what we do is we try to figure out how to get a starting point. Maybe we have a model that's learned from human data what humans do. So the AlphaStar effort on StarCraft kind of worked this way, where they gave it human games playing StarCraft, and that got it started knowing kind of how to play a game. And then you're also going to rely on the fact that you figured out which of the moves they took were useful. Same deal for rewards. Reward models in general, there's a lot of things you can do. You can figure out if it's a good game or a bad game, but you can also ask human judgment, and you can train classifiers. You can use other sources of information to really improve this part. And so I'll go into a few ideas here. One of them is going to be self-play and human judgment as like ways in which we're trying to do this with language models or games. But it's sort of another place in which we have to crack a lot of problems to get good. So again, this is more of like an overview, but it's just to give a sense of like one popular algorithm that gets used a lot in reinforcement learning these days. It's called proximal policy optimization. So the big idea with proximal policy optimization is that it's a policy gradient method. So we're going to be taking different moves. And what we're going to ask a neural network to do is to choose among a series of actions. And so the actions are a bit like the tokens we would have a language model. We're going to give each one of them a probability. And every time it takes an action, it knows how likely it was to take that action. At the end of let's say, of a maze or some specific series of moves, we're going to figure out whether it did a good job or a bad job. And assuming we do this well, we're going to get some amount of reward that comes back. And we're going to use the difference between how well did the model believe it was going to do and how well it did in practice to then increase or decrease the likelihood of the actions it took. And that measure, that difference between the expected return and what actually happened, is called the advantage, which essentially means you take a move and you thought it wasn't going to be good. OK, great. It happened as expected, but it did something better than expected. Then let's increase the probability of doing that. So PPO works this way. Generally, we sort of assume that all these things are going to kind of learn at the same pace. Of course, it's sometimes harder to learn the expected reward, or sometimes there are too many actions, and that makes it really hard to learn. But this has just been kind of a valid starting recipe for many problems. Now, we have a very weird specificity, because we were talking about language models just before, that many situations in the world, robots, games like that, have a hard time to be reset. Like if you're playing with someone online, you say, OK, let's go back in time and start the game over. That's not always a practical scenario. With language models, we usually have the ability to give it a starting prompt, a question, and to play the game multiple times, always from the same starting point, and to compare the outcomes. And that gives rise to something called GRPO or DAPO or Dr. GRPOs. There's a variety of methods like this. There's, in fact, a couple other acronyms that have come out recently. And they all rely on a slight twist on what we saw with PPO, where the actions here are going to be the different answers you could have. I'm putting this with a maze, but we can kind of imagine it with responses that a chatbot could emit. And each one of them is going to get some reward. And so rather than computing the expected reward and getting the difference, I'm going to simply look at the difference between the rewards I got. So my best response has a high advantage. My worst response has a low advantage. And so I don't need to predict rewards. I can simply look at how well my bag did. And that's what we call the group advantage. So this is a method that, while it seems very simple, has a clear advantage in that there are so many ways that things can go right or go wrong that it becomes a very hard problem to predict in practice how you're doing. So very convenient trick, and it's kind of led to a lot of the DeepSeek results and all these things there. OK, with that said, let me just take a step back. So reinforcement learning, kind of from a broad theory perspective, we've sort of seen what goes into it. Now, if we want to make this work in a bunch of different places, whether it's kind of games where the games are pretty sophisticated or getting it to work in industry, we have to sort of crack the practical version of these problems. So one example that I think is kind of informative here as we kind of look at like language models as another use case of long sequences and complicated rewards is getting really good at playing games. So one of the works that I worked on with a variety of other people back at OpenAI was a Dota 2 bot. And this one has a specificity that we didn't want to use human data to get good at it. And one of the tricks that we had is that we could get bots to play against themselves. And that method called self-play enables you to always have a winner, to always have kind of a paired opponent that's about as good or as bad as you are. And as you progress, there's always going to be one of them that won the game. And that let you basically bootstrap it to becoming a good agent. So that was one part of it. So that's the self-play as a natural curriculum part. And these curves here are basically how likely you are to play against one of your historical opponents. So as the game progresses, you start saying, well, this player that I used to play a long time ago, I no longer know how to beat it. And so you have this bit of a rock, paper, scissors system that happens, and you start returning in the past. Unfortunately, this isn't always the case with, let's say, areas where there isn't a two-player game. So we have to be mindful that this won't always save us. The other part here that I think is quite interesting is that reinforcement learning itself was a little bit treated as this weird branch of machine learning where things worked everywhere else, but then reinforcement learning, like all bets are off. You should do it batch size 1. You should not play this game, or this will never learn. In fact, the theory about this was that strategy could never come out of these bots. Like there's no way they could actually learn how to play it like a human. It's just not feasible. What we ended up kind of uncovering here, and then it had a lot of other interesting works that came after that sort of continued this, is the idea that scaling laws, so basically predictable behavior of the way that machine learning models will train and do, also applied in the case of data. And so we could sort of figure out exactly how much data and how old and how, basically how we should collect the data and how well that'll do in practice. And that let us basically say, okay, we need to scale our experiments to this size to get to this level of performance, rather than just throwing darts at the wall and seeing what sticks. So that's really sort of one of the important lessons here, is that we figured out some things around the fact that it's a noisy problem, but it can be mastered, and that data that becomes really old ends up actually hurting your system a lot more than people expected. So that's the freshness is exponentially good, or put the other way, any old data creates sort of exponential damage on your learning. We find these lessons to actually hold true also for robotics. So things that happened with robot hands sort of inherited a bit of those properties. And so we sort of applied the same things around sizing to make them work well. So more simulations, more data end up reducing the gradient noise. And the last one here is basically saying, if I have a specific compute budget, I can sort of figure out how many simulations, how big of a batch I want to do, given how long I want to run. And that gives you these sort of optimal returns. So you can kind of predict your investment, right? I have $100, how much do I put into one area or another, such that I get a good robot hand or Dota player. So now let's take a problem that like kind of looks a little bit different, but it's got similarities. At NVIDIA, we care a bit more about chips than we do about Dota, or at least we don't make Dota, we just care about running it. But in the chip world, we sort of thought, okay, what have we learned about reinforcement learning that can let us do better processor design? And this kind of goes back to the maze problem. We're looking at a problem in which we don't always have the solution. We have textbooks that give us some approximation for what is a good circuit to do an operation, but we don't have a perfect solution. So we can give a few samples and say, those are good, those are good. But human experts have a hard time reasoning about spaces that are this big. So we wanted to see if reinforcement learning could sort of etch its way into creating better solutions with this. And kind of applied similar lessons here around like the size of the simulation and the scale. But to give sort of a visual representation of what's going on, the depth here, so how short they are, ends up representing how fast of a circuit it is. And generally when they're longer, they have less of these points, and so they take up less area. So we have a trade-off in chips, whether we want them to be fast, but they'll consume more area. There'll basically be larger components to tap out on a chip, or these sort of components that will take a longer time to get through a specific process. And they'll force the clock cycle to run slower. So we want to find basically solutions that are best in both worlds, depending on where they're situated in the overall design. So the way that we worked on this was to basically get a neural network that would look at some design and predict little changes to them and always improve over initial circuit. And that's essentially this credit assignment story. It's that I have a circuit here, can I make it a smidge better, a smidge better, a smidge better? Or can I take a few leaps, but then in the end it'll pan out? So that's essentially how you could kind of convert these problems that were industrial back into the land of reinforcement learning and do it this way. Again, without human knowledge, right, we're sort of looking for new solutions that didn't exist. And one challenge I'm not going to go into here is that it's really slow to get these rewards. So Dota takes 45 minutes to do a game, or 2 hours. It's terrible, so you run it at a big scale. Turns out that these simulations are like, great, it's just math, we'll just figure it out. We actually have to figure out what the circuit will look like in a run design to be able to see if we're making progress. So that was sort of one of our main scaling challenges in these things, is not only getting models that run, but also ensuring that we can get good reward data. I guess there's a nice story here, and then I think the main question is sort of where are we going to take this next, is that we were able to get really good circuits with this, provided that we really went into realms in which humans were bad at doing things. When you look at sort of extremes, like circuits that run at a specific, the fastest you could get or the shortest you could get, we sort of have solutions that are okay. But if you wanted to have the entire continuum of solutions, I want one that does exactly this. What was amazing is we got basically models that designed the entire continuum of solutions that humans wouldn't have found. So that's essentially where we ended up being with these prefix RL circuits. And they're inside the Hopper H100s and the future generations. So it's sort of become one of the ways in which we create our designs now. So anyways, this is a paper that you can consult. So most of the parts that are specific here are going to be the cell designs and all this. But the reinforcement learning part, I really invite people to think about how their problems could run this way. So let me kind of switch to the language model land, because I think if we're talking about frontier, we sort of think about like, okay, what about reasoning models? What about these things? So at a high level, we have different areas in which we're using language models today to do things, whether it's coding, math, or just language or assistance. And the typical recipe that we've had so far that seems to work really well is basically get people asking questions and getting the right answer. And we just ask a model to predict that. So we have instruction data sets that do this. And that's basically where things kind of get a little bit distorted. So this is supposed to work really well, but it turns out that it's not really what we care about as users of these systems. It turns out that like maximizing the likelihood of prompt output pairs is actually just optimizing for good transitions. I'm at this point and I want to go to this point. It doesn't actually optimize for whether or not in the end the dialogue or the conversation or the thing ends in a good position for an end user or for the health of the system, let's say as a whole. The way to understand this is that in practice, LLMs are sampled. They don't always give the same answer. And that basically accumulates errors, it creates drift, and it gets you farther and farther away from typical known behavior. And maximum likelihood basically covers the training data. It doesn't necessarily tell you how to minimize the worst case scenario. So when we look at that, we say, okay, great, we can maybe use reinforcement learning here to help this, although we don't really have a human in a box that can do the rewards, so it's going to be a little bit harder, but at least this is the motivation for why we can't just do supervised learning and call it a day. So when we try to convert this problem back to something that can be done with reinforcement learning, one effective strategy was essentially to take the same kind of instruction data sets we had, a model that started out being pretty good so that it doesn't just give you garble at the beginning, and have it generate a lot of sentences. And then we could use PPO in this case with a classifier that says a human likes this answer or doesn't like this answer. And so now what we're doing is we're saying, even if the model samples, we ensure that it limits the worst case scenario, or it lands in places where people are happy or they're okay with an answer. If it invents something and then it apologizes, that's all right. That's favored over an answer where it doesn't give you that sort of benefit of the doubt in a way. So that's really where we start out with things like RLHF, and then there were variants of these methods, like let's say SteerLM or DPO, that went into ways in which we could use existing offline data, so ways in which people have given instructions, but we convert them into, okay, but mitigate the worst case scenario, improve the best case scenario, be polite, things like that. These aren't really creativity-seeking problems, but they're ones where we essentially deal with the fact that at deployment time, these are going to be a bit different. Now, there is something a little bit limiting about this that I think maybe some people have some experience with, where if you ask a model to give you the logic behind its work, what's generally kind of called like the chain of thought, it'll give you very different answers, and sometimes a lot better answers. But in a world in which what you're being judged on is an exact response, so you had to respond with 10 if I was telling you what's 5 plus 5, there isn't any room for that kind of behavior. So scratch pads and sort of basically these like reasoning models essentially open that up by creating a place where the model could basically wander a maze before it gave you its answer. So again, if you've seen all this, I'm just kind of giving it as context, but the way that it works is that in the model's response, some of the tokens are marked as being out of bounds or sort of things that will not be judged directly. They just get to do what they want in those tokens, and they can sort of emit a thought process or some notes or something about what they're going to do. So if we ask it what's the derivative of 3x plus 2, it might in there say, I recall the derivative rule is such and such, and then give you the answer. And that tends to give it more like quote unquote breathing room for doing things. And so this has given rise to like sort of many exciting results, like the O1 and O3 models, the DeepSeek results, things like that, where we sort of see them start to exploit this current area where, back to emergence, we don't know what we're supposed to put in those think tokens. We're sort of letting it figure it out. So starting from this, I think we can go back to like practical use cases. So we now have models that are able to use these think tokens, and they're able to apply them. And we start to get them to do sort of interesting things in the real world. One example of this is something called SWE-bench, where people took real GitHub issues and turned them into a data set where we're going to ask LLMs, however they're deployed, to be able to write real code that will solve an issue. Unfortunately, this is no longer kind of a clean setup in which you just have like a little prompt and an answer. You have to sort of connect it up into many pieces to get the answer to work fully. But you know, despite that, you can still sort of make some progress on it. So when we use these models that are trained with reinforcement learning and all this, they're not actually perfect at this, but they can be adapted to it. We can basically prompt them in a really smart way to get them to be very good at this. So one of the ways in which we found that we could develop things that work really well, that are pretty simple, because there's all sorts of different techniques there, was to essentially figure out inside of a code base relevant pieces of context, or snippets of code that would be relevant. And then we ask a model to filter through those and to build up the best possible context we could for the LLM. Once we have this, we ask multiple different models for a response. And it's basically the collection of different models that ends up providing the best fixes for the code. And that kind of goes a little bit into sort of a weird specificity of the models, is that we want them to be able to find commonalities between different reasonings. Like one model might be correct some amount of the time, but if many of them disagree or many of them agree, we can use that as a strong signal and we can create even stronger systems out there. So that's very much what the Nemotron Cortexa work does. And I think when we look at like test time compute as sort of a strategy, it's essentially building upon that. It's sort of asking models to have more samples and more abilities to bet on an outcome and to use that accumulation to reduce errors in the systems. So we can get them to go a lot farther by expending compute in this way. So using this, we're able to get to progress on, let's say, common code issues, things like that. And it sort of begs the question, like, sort of where can we take this in the future? So things that break and things that were kind of upcoming here, one of them I'd say is kind of vexing, is that reinforcement learning today is a very small part of the compute. So that's why I put pre-training here, is we sort of wonder, well, how do we make this, how do we make reasoning a more integral part of the way that the models learn? There's new knowledge. Essentially, there's a belief that like reinforcement learning isn't doing anything. That we're just simply taking a language model and slightly reducing its odds of doing something bad, but it's not actually coming up with new solutions. Like whatever it did was somewhere in the training data, and like, it's just an inefficient training algorithm. And then there's another one, which is basically how do we basically scale these things up, right? A lot of what we've done so far is so incredibly costly that we're sort of touching the surface of it. But in order to make it kind of as big as we did with pre-training, we have sort of new challenges ahead. So to kind of go into that, I'll just sort of motivate by saying, when we look at like the scale of things that we do with models, the x-axis here could be basically how costly or how complex it is to get data or to solve a specific problem. Or even in the case of code, like how long does it take to execute a solution? If it's beyond the realm of, let's say, 100K tokens or something like that, we start to be beyond the training data domain. So the models are sort of generalizing, somewhat okay, we can kind of push it farther, but it's hard to go in that direction. And then there's the kind of a y-axis here going up where we sort of think about the skill ceiling. Like many things that we want to do with models could be at the level of a human. I just want you to respond to an email as good as I would. Or there's things where we really want them to be beyond what a typical person or an expert could do. And I think that's what we're sort of looking for, like the Millennium Prize or competitive programming, or the prefix circuits that I was showing before, where we're saying, experts aren't even in the realm here, so we want this extra generalization beyond that. We want to be able to use compute to make smarter systems than the ones that we brought in. So the two sort of big goals here, right? So skill ceiling and kind of pushing out our ability to run on more complicated tasks or be more sample efficient with the data we have. So as I said, like pre-training is one of those areas where we sort of see an opportunity because we don't really know how to do it well today. We do it with a lot of pre-training data, and at the end we'll do supervised learning or reinforcement learning to get them to be good chatbots or good science models, things like that. But in a world in which we could actually spend a lot of time with these models interacting with systems, with code, with real world, we could get to a world in which they learn by themselves to become much better systems. So there's many difficulties in this place. Basically, one of them is that most of the world is not designed to give you nice rewards. Like as humans, we learn by trial and error. It's a complicated problem. But in our case, there's recent work here where you can experiment with the idea that the model can hint itself and say, if I think about the problem in this way, I'm more likely to predict the next token. It's very generic, but it gives it an information source, an information reward. And that lets it start to do the reasoning part way earlier in the training. So that's something called RLP, or reasoning at pre-training time. And it gives a boost in basically the pre-training phase. Everything that gets SFT'd after does better. And some way to think about it is that you've warm-started your reasoning process. So we're not completely there yet. This should be scaled up, but that's sort of a hint that there might be something in that area that could be done. One of them I'll mention just because I think it's kind of funny because there isn't really sort of a fully answered question here. When you do reinforcement learning with models, they have this weird behavior where they'll get better and better, and at some point they sort of plateau, and you're like wondering what's broken about them. And there's work where basically they went into asking, at the very beginning of training, your initial model that didn't go through any reinforcement learning, how well can it acquire knowledge? Sort of how far away was it from knowing the right answer? And the blue curves here are essentially showing as you give it more samples, right, you sort of explore all the things that were within the realm of likely answers they could have given, how likely is it to stumble upon correct answers? And with reinforcement learning, you're basically going to change that curve. You're going to make it more likely to get good answers early. But if we look at the sort of extreme right part here, there's many areas where the blue and the orange meet, essentially places where the advantages you thought you got out of reinforcement learning might not exist. They're basically just pushing up things that were already there. There's no discovery, there's no emergence. We're not finding the same things that we really wanted out of reinforcement learning. So when the authors of this work actually went into a little bit more depth here, they found that actually you get a lot of weird things coming out of reinforcement learning. One of them is that they actually do get better at code. So that's one area in which there is sort of quote unquote emergence. And the other area is that the reasoning part, the sort of the things that they put in their think tokens, were initially mostly wrong, sort of invented explanations that the model would put. And as you train farther and farther, we can see that basically the orange and blue curves don't match anymore. What's happening is that it's starting to use that stuff for something productive. So we basically have models that are able to use that space to do something. So let me kind of give a quick note on what we can do about scaling. So at NVIDIA, we sort of care a lot about enabling these systems to get a lot bigger, and that's kind of what we've done with Megatron and what we're currently working on with Megatron RL. And one of the ways in which we've thought about this problem is to say that there's trade-offs that are being made in how much computing power you're going to put into training the models versus how much you're going to put into collecting data at the same time. And even when those systems are sort of well-tuned, there's no waste, there's still a trade-off that's happening where if you have an oversupply of data that might be older, that might be longer, you're going to end up doing very different things to your training. So if we look at the scaling laws that we sort of discovered in other problems, we can basically color these plots by the efficiency that we would get. So how fast of a train do we get under different setups? So if we have small models, small language models, we find that basically there is an advantage to being towards the right on the more inference GPUs. Basically, you don't need a lot of training power. You can sort of afford to run on smaller batch sizes and have less training, but you benefit from getting a lot more data that you get to run through, many more environment samples. And that's sort of what a system should allow you to do. As we get to bigger models, this is a little bit different. We start to have an entire space in which you might as well put all of it into training. Environments are slow, but training is really slow, and they're both worthwhile. Now, to our point about scaling and how the world's going to look like in the future, tasks that we'd run with language models are sometimes answering a short question, and sometimes they're doing much longer tasks. So the vertical axis here is saying, well, what if the problems that you're trying to solve with your language models take a really long time to run? What happens then? And we sort of see that in all cases, we're going to start to need a lot more computation power to be allocated to just doing inference, to just providing a good amount of experience data to these models to train, whether we're in the small or in the big regime. So this is kind of one of the motivations for work that we've been doing on building a system that is currently being open sourced, and it'll kind of go through evolutions, but just to give kind of a sense of what it's doing. So the left is the typical RL infrastructure that people have. You train and you collect data on the side, and that setup is kind of nice. You get to increase a lot of the data collection arbitrarily next to your training, and you feed it in. But it's always a little bit delayed because basically training and collection happen at the same time. And there's an aggregated setup, which is the one that we're sort of advocating, where you can actually combine them, and you can create these much tighter systems where you have much more training power and inference power at the same time without having older data. And a system that allows you to dial between the two is a system that allows you to visit the entire curve here, to work towards problems that are going to be longer or work towards problems that require big models. So this is still being worked on, but this is something that we're pretty excited about for the moment. It's already seeing some speed-ups on it. So that's Megatron RL, and it's one of the engines that goes into other RL environments that we work on. For instance, something that's called Nemo RL is also something that we're open sourcing, and we're hoping that people get to use and do exciting things with. And this one has a focus on basically taking those ideas, but making them really accessible to train all sorts of models at low precision or on things that you might find on Hugging Face transformers, things like that. So that's basically Nemo RL that's going to basically hopefully help people work on this next scale of problems with reinforcement learning and language models. And maybe to close it out, thank you so much to the organizers for having me. There's links to the GitHubs for these code repositories if you want to check them out. And I kind of invite people to go look at these systems and try them out and try any of the models that have been put out by the Nemotron effort as well. And yeah, thank you very much.
Yeah, big round of applause for Jonathan. That was a fascinating presentation. Thank you so much.